Okay, students, welcome to video class 23. And here also we are going to deal with root locus, stability analysis root locus, part 2. Okay, so in the last class we have done some examples to give you a feel of what root locus is. Okay, so as in the example 1, we have what we did is we have actually from the given open loop transfer function, okay, we found out the characteristic equation, and from the characteristic equation we found out the root in terms of the forward path gain, and we went on to change the value of k from 0 to infinity, and we got for different values of k, the roots, the location of the roots is changing, and the path that the root travels as k varies is what is called as a root locus. Okay, that's what we studied, and we have also studied some two important points, that is the open loop poles always starts from an the root locus always starts from the open loop poles, and in this example there is one open loop pole, right? There is one open loop pole in this example, that is s is equal to -1. So this is one single open loop pole. So we have seen that in this root locus starts from -1. Now why it is called as a starting point? Because it is the point corresponding to k is equal to 0. Now we went on to do the second example. In the second example, what we have seen is it's a slightly different example. Here we have two open loops poles, right? And since it is two open, it's having two open loop poles, when you frame up the characteristic equation, you found out this to be a quadratic equation, showing that this has two roots, that is s1 and s2. Okay, now if you want to plot this roots, right? That's the meaning of root locus. That's how you find out root locus, right? So you have got, say, s1 and s2. So that means you have two roots, and these two roots will vary according to k. So as varies, we have found out some s1, s2, and here also we have seen that the root locus starts always from the open loop poles, and we know that the open loop poles is 0 and -4. When you substitute k is equal to 0, we have seen that both s1 and s2 starts from -4, and s1 starts from at 0, which is obviously the open loop poles. So this is made very clear, that is, a root locus always starts from the open loop pole. So in order to ascertain the stability of a system using root locus, you don't require the characteristic equation, you just require the open loop transfer function. Now this I am showing you just to give you a feel of root locus. This is not the real procedure. Okay, now I'll give you one more example to show something more about this root locus, and then we will be going into the real procedure of finding out or obtaining the root locus from a given open loop transfer function. Do remember, from a given open loop transfer function, it is not a characteristic equation. Okay, right. Okay, now consider a open loop transfer function given by k by s into s plus 1 into s plus 3. Okay, now before going into that, we know what are the open loop poles. Open loop poles is s is equal to 0, s is equal to -1, s is equal to -3. How will you find out the poles? Putting the denominator to 0. So each factor to 0, you will be getting s is equal to 0, s is equal to -1, and s is equal to -3. Okay, now the next is we are going to find out g is hs, 1 plus g is hs. Okay, so that is equal to 0, or you can make this 1 plus 1 plus k divided by s into s plus 1 into s plus 3 is equal to 0, and you may just take the LCM, and finally you will be getting, simplifying this, you will get an equation of a third order polynomial, which is 6 cube plus 4s square plus 3s plus k is equal to 0, right? So that means from this characteristic equation, you know that you will be having three roots, right? So we are going to find out those three roots, S1, S2, and S3, based on the different values of k. Okay, so you can solve these roots. Say you will be getting some S1, you'll be getting S1, S2, and S3 in terms of k values. You may find it by yourself. Okay, so you will be getting those roots as and substituting those values for k, these values for k into these equations. You will be getting a table like this. So I have done the table for you. So at k is equal to 0, S1, S2, look at the position of S1, S2 and S3. S1 is 0, S2 is minus 1, S3 is minus 3, which is in turn what? In turn the open loop hole. So k is equal to 0 is the starting point of the root locus, right? The starting point of the root locus. So how many roots you will be having? You will be having three roots. So you can come to another conclusion. The number of roots is equal to the number of open loop poles. So if you have an open loop transfer function, if you find out the roots, how many number of roots, that much root locus will it have. So every root lock, each root starts from its corresponding open loop poles, right? So now we have to draw this graph, right? Now when you draw the graph, you can say start with, first of all, you may just mark these open loop poles. How many poles you have? You have three poles. One is at 0, other one is at minus 1, other one is at minus 3, right? Minus 3, minus 1, and 0, right? So this is it. So this is the S plane. Now let's try to plot. So these are the points at k is equal to 0, right? These are the points at k is equal to 0. So this corresponds to k is equal to 0. This corresponds to again k is equal to 0. So at k is equal to 0, root locus, there three roots emerges, right? Three root starts. That is from minus 3, from minus 1, and from 0. Now we want to know how it goes. So look at this. As see, I have just arbitrarily selected another value called as 0.63. So okay, so before that you need to find out the S1 and S2 and S3 in terms of k. So that you may do it by yourself. That is the factors. Now apply into that. When you substitute, you can see that the S1 and S2 comes at a point called as minus 0.45 at k is equal to 0.631, right? At k is equal to 0.631, these two meets. So what's the meaning of this? This root, that is this open loop hole, actually this root moves in this direction while this moves in this direction and meet at a point minus 0.45. That's the meaning of this. See, it starts from 0, another one starts from minus 1, and the next point at 0.631 is minus 0.45, so it meets. As I told you earlier, again there is a tussle or a war between each, and that means it collides and it won't stay there. It has to break up. That's called as breaking up. Okay, so at this point something happens, and that is what is called as a breaking up of the root. Okay, if there is a tussle, definitely there must be a breakup. So it breaks up and it goes into two different directions, and that's what 5 suggests. At 5, what happens? Now remember at 0.631, what's the value of S3? S3 is moving towards this side, right? So this is minus 3, the next one is minus 3.1, and this is the value at k is equal to 0.631, right? Now this has reached here, and what's the value at 5? Now as at 5, S3 again moves further along the real axis again to in the negative direction, minus 3.55. Okay, what about this? This breaks up and moves into the imaginary axis. Now S1 is actually moving towards minus 0.27. This is minus Okay, so here from this it breaks. Now at k is equal to 5, you got a point called as minus 0.27. What is minus 0.27? It may come around here, right? So this is minus 0.27. Say call this as j.98, and this will be j minus 0.98, right? So this is minus 0.27. This is also minus 0.27. So this actually the next point, that this is the point obtained at k is equal to 5. So k is being varied from 0 to 0.631, and it gets varied, and we know that at this break it breaks up and it moves. So in the previous example I have seen it as a perpendicular, in a perpendicular way, right? It moves straight, right? It breaks into straight, but this value suggests that this at k is equal to 5, this point, the root that comes from here actually moves here at k is equal to 5. So we need to draw in this fashion, right? So similarly, the the root that comes over here breaks in this way, right? Breaks in this way, right? Now what if I increase the value to 12? When I increase the value to 12, this reaches a point called as j 1.732. This reaches a point called as minus j 1.732, right? Okay, and this is at k is equal to 12. This is at k is equal to 12. Now what's the situation of S3? S3 becomes moves towards the negative side. Again it moves to 4.1. So we have seen that as k varies, this S3 remains always on the real half but in the negative direction. Okay, so you can see that at infinity this reaches at minus infinity. Okay, so this is going towards the minus infinity side. While what about this? As at k is equal to 40, k is equal to 40, S3 becomes minus 5, right? So that's why I told you it won't go away from this real axis. It remains on the real axis but in the negative direction. While at j is equal to 0.5, look at this, look at the value. Both are positive. That means it comes in these two quadrants, right? 0.5 plus j 2.4, 0.5 minus, so that will be somewhere over here, right? 0.5, 0.5, and this will be somewhere over here. So this moves in this way, right? Okay. Now what can you say about the stability of the system? This system is stable till k is equal to 12. Am I right? What happens after k? Just after k, this root locus goes into the right half. Okay, so that the system becomes unstable. So, can you call this system as a totally an unstable system? No, this system is not an unstable system for all the values of k. For the values which is designed up to 12, from 0 to 12, the system is a stable system. While after 12, what happens? After 12, it crosses the imaginary axis and goes into the... So, by this analysis, so that's why I told you, root locus is not giving you an yes or no answer to the question whether the system is stable. It gives you more information. And now, can you provide any restriction to the system so that the system becomes stable? Yes. What's the restriction? The restriction is design the system in such a way that k must be less than 12. Right? Hope you understood. This is it. And I will give you one more example. And now so far we have learned all the examples. Just look at those examples which we studied earlier and this time. All the examples, we haven't considered anything about zeros. Now I'll give you one more example with an open loop transfer function with a zero, as well as with an open loop zero and open loop poles. So far we have studied only the open loop poles. What's going to be the effect when zeros are there in an open loop transfer function? Now look at this example 4. You have an open loop transfer function GSHS is equal to k into s plus 2 divided by s plus 1. So you have zeros here. Say z is equal to -2. So s is a 0 and you have a pole, an open loop pole at -1. Okay, now let's move on the same procedure which we have so far done. Find out GSHS is equal to 0, which is the characteristic equation. Now the characteristic equation, you will be getting this as S plus K into S plus Ks plus 2k plus 1. 2k plus 1 is equal to 0. So this is what you are going to get as the characteristic equation. Now from this you can find out S. Right, this is very simple. You can find out S, and the S will be minus of 2k plus 1. You may find it by yourself. Minus 2k plus 1 by 1 plus k. Now as earlier, I am just going to put some values for k and finding out various values of s. Okay, right? Okay. Okay, look at this. When you put k is equal to 0, what's the answer? When you put k is equal to 0, this is 0, so this will be minus 1. When k is equal to 4, this becomes 8. 8 plus 1, 9 divided by 5, right? So that is minus 1.8. And just put 9, see that this is minus 1.9. 99, it becomes 1 minus 1.9888. So it's remaining at minus 1, right? Now what happens at infinity? Infinity, this becomes an infinity by infinity form. So at that time, what you should do is you should you should apply L'Hospital's rule, that is differentiating both the sides individually, right? So when you differentiate this, this becomes minus 2, numerator, denominator, this becomes 1, right? So this becomes minus 2. Or you can take k outside, or you can do in this way. When you take k outside, minus k outside, this is 2 plus 1 by k divided by k into 1 plus 1 by k plus 1, right? So this k and k cancel, k tends to infinity. When you apply k tends to infinity, this becomes 0. So the answer is going to be minus 2. Whatever way you need to, you can find out. So you'll get this as minus 2. Okay, so the ending point is, the terminating point is k is equal to infinity. The starting point is k is equal to 0. So now look at this. This is an interesting thing. So s is equal to, so k is at k is equal to 0, s is equal to minus 1. What is s is equal to minus 1? S is equal to minus 1 in turn turns out to be what? Turns out to be the, as always, turns out to be the location of the open loop poles. So at this is at minus 1. Okay. And what you can see is at z is equal to z is equal to minus 2, you have a 0, right? Z is equal to minus 2, you have a 0. So you can just simply mark that as 0. So this is how we plot pole 0 plot. This is at minus 2, this is at minus 1. Now let us see what happens as k increases. K increases, this becomes minus 1.8, right? So at k is equal to 4, so that means from this values you can see that the s always remains on the real axis. It won't go into the imaginary area, right? So that means this lies in between minus 1 and minus 2, right? So this is minus 1, and you can say that so it's going closer and closer. So this becomes minus 1.8. So this is the point at k is equal to 4, and k is equal to 9, it becomes more closer. K is equal to 99, it gives more and more closer. And at minus 2, it comes to at at infinity. At k is equal to infinity, this has reached the point where a 0 is placed. Okay, so here in this root locus, so what is a root locus? Root locus will be, you can okay, so this will be your root locus. This is your root locus. The root locus starts from this minus 1 and terminates at 0. So far we have studied that, it terminates at k. I mean, when k is equal to infinity, it may either go to infinity or at some other places, right? While what you infer from this is this root locus terminates either at infinity. There are two options. So far we have studied in the previous example, just seen, we have just seen that in the previous example. Look at this. Now, what's going to be this value at k is equal to, definitely it's going to be at a point called as say infinity plus j infinity. This will be minus infinity minus j infinity, right? So it will be going in this way. So as at k is equal to infinity. Now in this problem, at k is equal to infinity, this root comes at minus 2, or you can say that a all root locus starts from where? Starts from an open loop pole, while root locus terminates either at a 0 as in this example or at infinity. Okay, so these are the two things that you can derive or can conclude from this problem. Okay, now so far what we studied is we just try to draw the root locus from a given open loop transfer function. Okay, what we did is we found out the characteristic equation and we found out the root in terms of the forward path gain, and we varied the values of k. We have found out that this is actually, it starts from the open loop poles, proving that you don't require these evaluation to obtain the root locus if you have a specific procedure, right? So what will happen to, I mean, what's the drawback of this method? Now, as this becomes complex, right, as the GSHS becomes complex, you are going to get, as we have done in this previous example, this is a bit more complex than the previous one, so the equation becomes of the higher order. Now as the equation becomes more and more complex, it's very difficult to factorize that, and it's very difficult to find out the roots and to ascertain about the stability of the system. So you have a procedure which uses only the open loop transfer function of a closed loop system to ascertain. So from this open loop transfer function, if you follow that procedure, you will get the same information as we have derived here, right? So you don't require to solve this big characteristic equation. Okay, so that's what we are going to study next. That's the real procedure. So far we have just studied just to give you a meaning about root locus. So in the last example, in this example, we have seen that root locus starts from an open loop pulse and it terminates at an open loop 0. Okay, so from this we concluded that root locus starts from an open loop pole, but it can terminate either at 0 or at infinity as in the previous examples. Okay. Okay, now let us straight away go into a problem of a root locus with procedure. I am going to explain this problem by the explaining the procedures of how to do this problem, right? In a stepwise way. Okay. So be very careful in following each steps, and after doing this problem, we will list some of the salient features of this root locus, which is a very important topic, which may be asked as a theoretical question. Sometimes they may be asking you explain or list the salient features of root locus. Okay. Anyway, so far we have studied in the previous example some of the features are, one is about the starting point. We know that the root locus always starts from an open pulse and it terminates either at 0 or at infinity. That's what we studied. And in general, you need to understand that for a control system, this is a topic which is to be told, which is to be covered earlier, but you may just listen to this. This is just a topic which you need to understand. That is, normally the number of poles of a system is equal to number of zeros, right? So in this example, how many poles are there? You have p is equal to, let us call the number of poles to be p and number of zeros to be z. So in the above example, p is equal to 2, right? And what are those poles? That is equating to 0. You will get s is equal to 0 and s is equal to minus 4. These are the poles. Now what about the zeros? The number of zeros is z, and this is the letter that we are going to use in this root locus as well for the number of poles and number of zeros. So the z is actually equal to 0, right? So in the open loop system, in an open loop transfer function, from the open loop transfer function, we found out the poles to be 2 and poles to be zeros to be 0. But I told you, generally, the always for every system, the number of poles is equal to number of zeros. So how will you correlate this? We know that P is not equal to Z. So what's the meaning of this? The meaning of this is, if you have poles 2, we need to assume that there are zeros at infinity. So that's why root locus terminates at infinity. So root locus always starts from pole in search of what? So just as we you might have studied in your studying in your EM theory, that is about dipole, right? If there is no negative charge, you have a positive charge and a negative charge. If there is no negative charge near, this will be emanating the field, the electric field in this direction. The positive charge will be radiating its electric field around this in an omnidirectional path. Now, once if you bring a negative charge close to this field tends to move in this direction, right? 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 So this is it. So always a positive. So if you keep a positive charge isolated, it will radiate its field around it, all around it. This is called as an omnidirectional pattern. Now this positive charge is moving towards infinity in search of what? In search of negative. So this is moving this is emanating its field in under the assumption that a negative charge is placed somewhere at the infinity. Similarly, a pole, when it starts, it goes in search of zeros. Okay, right? So at this time, you can see that if you have a two poles, then this system must have a zeros at the infinity. That's why a root locus starts from a pole, and if there are no zeros in that system, then that goes to infinity. Those poles will go to infinity in search of zeros. Or if there would have been zeros, then all the poles will terminate at a 0. That's the logic. Now, as you have seen in this example, right? Say you have a pole and a 0. This pole is never going to infinity. Why? Near this pole you have a 0. So definitely this pole will be moving towards 0, just as a positive charge moves towards the negative charge. Hope things are clear. Okay. Now let's move on to the problem. So the first part is draw the root locus. So in order to draw the root locus, the first step is identify the open loop poles and zeros. Okay, open loop poles and zeros. So that you will get from this open loop transfer function and a unity feedback control system. I'm again explaining that means h of s is equal to 1. So this is actually GSHS because hs is equal to 1. So the transfer function is given by k is equal to k by s into s plus 4. Now from this observation you can see that the number of zeros is equal to 0 while poles is equal to 2. And what are those poles? Let us designate that pole as P1 and P2. Equating this to 0, you will get P1 to be equal to 0, P2 to be equal to minus 4. So this is it, right? So this is step 1, identifying the open loop poles and zeros. And the next step is to have the you should have that graph. So in the graph you may just draw or represent this pole zero plot. So that's a step that has to identify the open loop poles and zeros and plot the pole zero plot. Pole zero plot, or obtain pole zero plot. Okay, this is very simple. Okay, so in your graph sheet, a normal graph sheet, what you can do is, okay, you can just mark one as 0, the other one as, this will be -1, -2, and minus 3 and minus 4. Okay, you can mark in the normal graph sheet. Okay, now at 0 you have a pole. The pole is marked by into in a pole 0 plot, and you have another pole at residing at minus 4. That is also another pole. Okay, so you can mark that in your, this you must do in a graph sheet. This I'm just doing it for the explanation sake. You need to do it in a graph sheet. Okay, so mark the each divisions as minus 1, minus 2, minus 3 and minus 4, the main divisions, right? Not the subdivisions, as minus 1, minus 2. This is 1, 2, 3, and this is immaterial. You just require only the negative time. So try to draw this imaginary axis towards the right of the graph. Okay, so because almost all the poles are residing on the negative side, so always try to draw in that way. Okay, now so that's your step 1. We have identified the open loop poles and obtained the pole 0 plot. Okay, so you can take a graph paper, and this is what I told you. So to the right side, draw this imaginary axis towards the right side, because we are dealing with almost all the poles which is on the negative side. So you need a more space in the negative side. So that's why I told you the imaginary axis has to be towards, is to be drawn towards the more towards the right of this graph. Okay, so now you have this okay, this graph, and you can mark this as a j omega axis. This is minus j omega axis. This is actually sigma axis or minus sigma axis, and okay, this can, okay, you can just draw for just so this is positive sigma, right? Now this is these are the axes, so you need to mark this axis, and okay, let's draw this diagram, right? And let us mark the points. So this is your 0 point, obviously that's the origin. This one represents 1, this one is 2, this one is 3, and this one is 4, but with a minus, right? A negative sign, minus 3, minus 4, minus 5, and it goes on like that. Okay, right? Now in this in the positive direction, you just mark. You don't need, for this problem you don't require this anyway. You may just plot like this. So this is 2, 3 and so on. So what is this? These are the real terms. So these are the area where the real term is positive, these are the area where the real term is negative, and we want the system to have its root locus always on this half. So this is actually an S-plane, right? So this is actually a figure of an S-plane, and we are actually locus on this S-plane, and we want all the root locus, or the every point on the root locus should remain on the left half for the system to be stable. That's our objective. Okay, so we are going to see that whether this transfer function will be having such a graph or not. Okay, now that's the first step, and in the first step I have already told you to identify the open loop poles and obtain the pole 0 plot. Now you have poles at 0 and poles at minus 4. So how will you mark this poles at 0? Poles at 0 is usually marked by, and poles are usually marked by an into sign, right? This is an into sign, and at minus 4 you have another pole at minus 4. Okay, so as I told you earlier, what does this what notion you should get? That is the number of, for normally number of poles has to be equal to number of zeros. That means here in this case you have only 2 open loop zeros. Then what about the open loop poles? Open loop poles. So what about the open loop zeros? So normally for any system the number of poles has to be equal to number of zeros. That means you need to believe that the other 2 zeros, okay, so these 2 poles will be moving in a particular direction to, in search of what? In search of zeros. So how many zeros will be there? There will be 2 zeros, but residing both those 2 zeros will be at infinities, and that infinity can be plus infinity or minus infinity. Okay, so that means how many root locus that you can predict. So a root locus is completed This is it. It starts from a pole and it ends at a 0, right? Right? So if you have a pole 0 pair, that means you will have a one root locus. Now here in this case, you have two poles. That means you have two root locus starting from these two poles, right? Now imagine, so I'll just give you ask you one more question. Now suppose you have another scenario where you have say two zeros, and one pole. Suppose if this is the scenario, what's going to be the result? How many root locus will it have? Anyway, a root locus is formed by a pole 0 pair. So you have a pole 0 pair here. So that means you have a root locus due to this poles. Now what about this? So anyway, it requires a root locus. So this 0 will also start to believe just as the pole believed here. What? This 0 is having a pole at infinity. Anyway, this has to be true always. That is, the number of poles has to be equal to 0. So you need to believe that the poles lies at infinity and it will be coming towards the 0. Okay, so that you will understand when we do problems. Anyway, for the meantime, let's not make things more complex now. So this is it. So here in this problem, you have two open loop poles, one at 0, other at -4. So that means that is your so you have two root locus that can emanate from this. So that's your step 2. So this is your second step. That is, from the pole 0 plot, you have come to the second step. That is the poles. The poles which we have marked over here. Okay, this poles has to terminate at either infinities. Now, where are these infinities? These infinities can be in this direction. Say this root can go in this way, this root can go in this way, or this in this way, or in this way, or in this way, or in this way. So whatever ways it can move. So that we are not knowing. So that's why I told you, in order to understand its movement, we need to follow certain procedures. Okay, so without going to the characteristic equation. So that's step 2. Now in step 3, you can find out the number of root locus. That is what I have just explained. The number of root locus, right? Or you can call it as a root locus branch. Okay. So the root locus that starts from each pole can be referred as a root locus branch. Okay. So root loci, you will call that as a root loci. Root locus, loci that obtains from, that emanates, or that starts from two poles. So the number of root locus branches will be equal to number of poles or number of zeros, whichever is greater. Hope you understood what is the meaning of this. This is step 3. Now, whichever is greater means, what's the meaning of that? Whichever is greater. Say, in this example, in our example, you have p is equal to 2 and z is equal to 0. So here, p is greater. And in the scenario which I explained here, say, there can be a scenario something like this, right? You have two zeros and one pole. So how many root locus branches you can have? Anyway, so the root locus branches will be, so here p is equal to 1, z is equal to 2. So you have two root locus branches. So in this example, the p is equal to 2, z is equal to 0. So the number of root locus branch is equal to 2 because p is greater than z. Okay, so the number of root locus is equal to 2. Now what happens if p is equal to z? Suppose you can have two scenarios like this, say, right? You can have a scenario like this where p is equal to 2, z is equal to 2. So that means each pole is having each 0. It's okay. The problem is solved. That means you have two RL branches. Okay. So this is how you need to check the number of root locus branch. Okay, so in this example you have two root locus, right? One starts from s is equal to 0, other starts from s is equal to -4. Okay, now the fourth step is about the existence of root locus on real axis. Now, we have already plotted the Paul zero plot for this problem. Now, as I told you, every Paul will be moving as k varies. Okay, do you remember, as k varies, all Pauls will be moving in a particular direction. What is the objective of each motion? They will be moving in such a way that they will move in search of zeros, right? So anyway, for some time these poles will be taking its path along the real axis. So that means this particular pole can move in this direction or in this direction. Similarly, this pole can move in this direction as well as in this direction. So we need to know that whether there is any root locus branch on this root locus. For that, the procedure is, beyond a particular point, if you want to find out whether there is a root locus beyond a particular point, just check the number of poles and zeros beyond that particular point. Okay, so I will just explain. Okay, say for example, in this case you have this poles. Now I want to see that whether there is any root locus existing on this real axis. So what I need to do is, I'm placing my hand over here. Okay, so just imagine that I'm placing this pen on this. Okay, and see that the number of zeros on this axis here, that is number of zeros and poles, that is the sum of poles and zeros will be equal to 0, right? So if it is an if the number of poles and zeros is an even number, okay, if it is an even number, then there then there is no root locus on the right of that section. Okay, when you place a particular, so on the, this is the right section, right? So if the number of poles and zeros is an even quantity, then there is no root locus residing. Now coming to this, place a point over here. Now look at the right of this plane. How many poles and zeros? The sum of poles and zeros will be p plus z is equal to 1, which is an odd number. If it is an odd number, then meaning there exists what? There exists a root locus. Now come to this, a point just beyond this, you can see that there is, again you have only one log, right? Now coming at this point, look at this point. When you take this point and see the right of this point, you can see the number of roots is equal to 2, which is an even number. That means no root locus exists. So we have proved that these two roots will be moving in the opposite direction, right? That means it won't be going in this, because why? After this point you don't have any number of zeros, which is an even quantity. Now place a point over here. To the right you have number of zeros is equal to, or poles is equal to, an odd number up to this -4, and beyond this, if you make a consider a point, you can see that the number of poles and zeros is equal to even. Okay, so I will just write down the general aspect of this. Root locus exist, right? Root locus exist on the real axis, if the number of poles and zeros, the sum of the number of poles and zeros are odd. Okay, so in this example you have real axis over here. You have root locus on this section, right? no root locus. In this section, no root locus. In this section also, no root locus. Okay, hope you understood. Why? Because here you have even number of zeros. Now, here also you won't be having, because when you place a point over here, over this, when you look at the right of this, you have 2. So here also there is no root locus. So the root locus exists only for this point. Okay, hope you understood this. So we have studied that, this root locus. So that means this as well as this pole starts in this direction, right? Because there is no chance of will it go towards this, because there is no root locus branch, there is no provision for this pole to move in this direction. So as the case with this as well, this won't be going in this direction, because as per this rule, as per this procedure, there is no root locus. So both the roots will be starting in an opposite direction as shown in this figure. Okay. Okay. Now next is, now we have seen that this pole moves in this direction, this pole moves in this direction for a particular k. Now as we have seen in the previous examples, anyway this is going to meet at a particular point. For a particular k, both the poles comes at to a particular point, okay, and I told you that at that point that will break up, because they don't like to meet each other. So definitely one pole has to go away from the other pole, so they will break up and move into different directions. So we want to know, the first thing is the point at which they intersect each other. So that point where this poles breaks is called as the breakaway point. That is why away, because it's breaking and moving away from each other. So that's why it is called as a breakaway point. Now, how to find out the breakaway point? So we know that actually these poles moves in this direction as this movement is as k increases, right? Right, that's what we have seen in the previous example. So as k increases, what happens? These poles moves towards this direction, and it will be meeting at a particular point, and we know that that particular point corresponds to a particular k, right? Now, or as long as it stays, so that is the point on the real axis where k is maximum, right? On the real axis, I don't mean the imaginary axis. So after that value, this breaks up and moves to the imaginary side. That's going to happen, right? So we want to find out the maximum value of that k on the real axis. So how will you evaluate that? So for that, you can obtain the characteristic equation of this transfer function. Now what is the transfer function? It is the transfer function is given by, the open loop transfer function is k by s into s plus 4. Now what is the characteristic equation? So it's a unity feedback system, so hs equal to 1, so 1 plus gshs, okay, equal to 0 is the characteristic equation. Now you can simply find out this as 1 plus by k by s into s plus 4 is equal to 0, or you can find this as to be s square plus 4s plus k divided by s into s plus 4. S into s plus 4 is equal to 0, or the numerator is equal to 0. This is your characteristic equation, s square plus 4s plus k is equal to 0, right? Now from this you can find out the value of k, right? So now this k will be equal to k is equal to minus of s square plus 4s, right? K is equal to minus s square plus ks. Now what we want to find out is the value of this location where this k is maximum on the real axis. Now how will you find out the maximum value of k? Yeah, the maximum value, or you can see the value of s where k is maximum. How will you find that? That is differentiation. Okay, when you differentiate with respect to s and equate to 0, you will get the condition for maximum k on the real axis. Okay, Now beyond that, if k goes, then it will not be staying on the real axis, it's gone into the imaginary axis, right? So that is dk by ds is equal to 0, or when you differentiate this, you will get this as minus of 2s plus 4 is equal to 0, or 2s plus 4 is equal to 0, or s is equal to, right, 2s plus 4 is equal to 0, or 2s is equal to minus 4 by 2, s is equal to minus 4 by 2, or minus 2, right? Now this is what is called as the breakaway point. This is called as the breakaway point. Okay, so you can mark that breakaway point on the graph. Okay, so where is this minus 2? Minus 2 is this thing. So this is actually your breakaway point. Breakaway point at s is equal to minus 2, right? Okay, so this is the breakaway point. That means what you need to understand is this ball moves in this direction. Okay, this ball moves in this direction and it meets over here. Okay, and similarly this ball also moves in this direction and meets at minus 2. Okay, now this point is called as a breaking point. Now what is the next issue? So this is being governed by this method. Hope you understood how to find out the breakaway point. So from the characteristic equation, obtain k and find out the condition for the maximum k by differentiating it and equating to 0, you will get the breakaway point. S is equal to minus 2. Okay, now once you got that, next step is obviously this cannot stay here for long because they don't like each other, as I told you. So these balls, one of the ball will be moving in this direction, other one may be moving in this direction. Okay, but as I told you earlier, that this direction can be in this way or in this way or in this way. Similarly, the another ball can be in this way, or in this way. So how to understand that? For that, the first thing is we need to know an angle by which it moves. Okay, so angle that by which it moves. So then only you can understand. See, if it is moving in this way, this is the angle. If this is moving in this way, this is the angle. If this is moving in this way, this is the angle. So there is an approximate method called as the asymptotic method. That is, next is the sixth point. So this problem can be eliminated by drawing asymptote. Okay, now drawing asymptote means asymptote is just a straight line which actually guides this root locus, or which actually guides or gives an information regarding the direction of this root locus, so that this root locus can go parallel to this asymptote. It doesn't mean that it has to go exactly through that asymptote, but it can be a parallel line to this asymptote. Asymptote is simply a straight line, but root locus is a freehand drawing. It need not be always a pakka straight line, but this root locus will be parallel to that asymptote. So we need to find out that asymptote. Asymptote is simply a straight line. So before that, you need to find out the angle of asymptote. How this you need to draw this straight line. Okay, if the straight line is drawn in this way, you can see that this root locus will also go in this way. If the asymptote is in this direction, the root locus will move in this way. If this is in this direction, root locus will be moving this. So for that, we need to know the asymptote, because asymptote is actually the guide of the root locus in the imaginary area. Okay, till this point there was no problem, but now once it break up, this needs to move on, but when it starts to move, there is another problem: where to go, in which direction should I go? So that will be dictated by asymptote. You need to draw the asymptote. For drawing the asymptote, you need two things. One is the angle, right? The another one is the point of intersection of this asymptote on the real axis. It is not necessary that the point of asymptote always have to be equal to breakaway point, because it is just a guidance to the root locus. You will understand later what I meant by guidance. Okay, now first of all is the angle of asymptote. How to find out the angle of asymptote? Okay, the angle of asymptote is given by this expression 2k plus 1 into 180 divided by p minus z. K varies from 0 to 1 up to p minus z minus 1. So let us call this as say theta, right? Theta is to be the angle theta k. So first of all, what you need to find out the number of k's. K starts from 0 up to p minus z. What is p minus z? P is actually equal to 2 in this problem, and z is equal to 0. So what is p minus z? P minus z is 2. So this is 0 up to 2 minus 1, right? This is 2 minus 1, which is equal to 0 and 1. So that means you have two angles, that is theta 1 and theta 2. Obviously, logically, when you look at this also, you require two angles. Wow. Okay, one for the one of the poles in this direction, other in the other direction. So you require two angles. So that is what will be theta 1. Now in this case, theta 1 will be when k is equal to, okay, k, so theta 0 and theta 1, and that will be nice. So because k is equal to 0 and 1, so theta 0 is, putting k is equal to 0, you will get this as 180 by 2, right? This is 180 by 2, which is 90 degree, and theta 1 you will get this as 182. Theta 1 is 2 into 2 plus 1 into this is 3 into 180 divided by 2, which is actually equal to 270 degree. Okay, now one more point you need to understand is you just need to not only requires the angle of asymptote, but also require the point of intersection of that asymptote. Now that is the next one. So that is the meeting point, or the meeting point of asymptote, or the intersection point of the asymptote on the real axis. Okay, on the real axis, and that is very simple. Let us call that as x. X is equal to sigma poles minus sigma zeros by p minus z. What is p and z? P and z are the number of zeros, so you can straight away write that as 2 minus 0, 2. Now what is sigma poles? Now we have already found out the poles to be what? Poles in this case, pole is equal to p1 is 0 and minus 4. Just add these values. That's the meaning of sigma poles. Adding the values of poles and zeros. Now in this case there are no zeros, so sigma zeros will be 0. While in this case this will be 0 and minus 4. So adding 0 and minus 4, you will get this as minus 4 minus 0 by 2, or this is equal to minus 2. Okay, now the meeting point of the asymptote. Now look at this. It is so happened, it is not necessary that this minus, always this x has to be equal to the breakaway point. Look at that, this becomes equal to the breakaway point. This is the case with this problem only. Okay, it is not necessary that always the meeting point has to be equal to minus 2. So the things are, so if the meeting point of asymptote is equal to breakaway point, things are getting more and easier for us to draw the root locus. So the breakaway point is also at minus 2. Now you can draw the angle of it. Now you can do, after finding out these two, then you have the work in the graph paper. Okay, now how to draw that? How to draw this 90 degree and 270 degree? Okay, now always this is your axis, and this with respect to, you need to draw with respect to this the anti-clockwise direction. Do remember, anti-clockwise direction. Anti-clockwise direction is to be taken as positive angle. Clockwise direction has to be taken as a negative angle. So in this case, we have seen that theta 0 is 90. So I mean with respect to this point, right? Because why I am selecting this? Because this is the intersection point of that asymptote. With respect to this point, plus 90 will be in this way. So this is it, right? So how will you mark that? That means this is the asymptote, right? Asymptote. So this is the asymptote. Now what is the next asymptote? Then you have 270 degree. So the 270 degree will be calculated in this way. This is your 270 degree. So the asymptote will be in this direction, right? Asymptote will be in this direction, right? So you have the asymptote in these two directions, right? Now, since it is the breakaway point is minus 2 and the intersection point of the asymptote is minus 2, the roots will also follow. What is the need of this asymptote? Asymptote is actually the guide of this root locus from the breakaway point. So one will be led among this. One of them will be led in this direction, other one be led in this direction. Okay, hope you understood. So so this follows exactly in the line of this asymptote because this is exactly 90 degree. If it would have been, I mean, in the next problems we will see different cases than this. For the meantime, you just understand why you are following the same direction as that of the asymptote, because the breakaway point happens to be the same as that of the intersection point of the asymptote. So we believe that one of the roots will be moving in this direction, the other root will be moving in this direction. Do I need to know which root will be moving in this direction, the other one? No, you don't need. The only thing that what we need to know is whether any one of the roots comes at this side. That's all what we need. Now look at this. If the root locus moves in this direction, okay, if the root locus moves in this direction, what can you say about the stability of the system? We have already seen in that previous example by solving the characteristic equation, the same scenario. So this won't be as this will be going in this direction up to infinity. This will be going in this direction up to infinity. In search of what? In search of its corresponding zeros, assumed to be placed at infinity, right? So this pole, I mean, we are not sure whether this pole is moving in this direction or this pole, and that we don't have to know. The only thing is that these two poles will never cross the imaginary axis, so that you can simply say that this system is a stable system. Okay, this is a stable system. So that is what the first question. The question was to draw the root locus, and the question is not complete, I think. And ascertain about the stability. So the second part we will be doing in the next session. Okay, so here it is. Here you have the root locus, and from this you can come to a conclusion that is a stable system. Now how many steps we have seen? So these are the procedures. So you have identified the open loop poles, obtained the pole zero plot as in this graph. Then second point is poles terminate at the infinity. Since there are no open loop, terminate at infinity, you need to write something about the termination of each poles. So there are no open loop zeros. So we are assuming that at infinity you have zeros. Then you need to find out how many root locus branch is there. That is equal to number of poles, which is equal to number of zeros, whichever is greater. So in this example it is 2. So the number of root locus branches is equal to 2. Then you have the existence of real axis. Once you have plotted the pole zero plot, you need to know whether there is any branch lying on the real axis, and you know how to find out. Consider a point and look at the right part of that. Take the count of the number of poles and zeros, and you can see that if it is an odd number, then there exists that, and through that point root locus exists. If it is an even number, then no root locus exists. So from this we have seen that from this figure we have seen that in this case any points, I mean, the right part of this point will be always having a root locus till this point, right? because it will be odd. So that means we have forced to believe that these two poles moves in this particular direction will meet up at a point called as the breakaway point. And how to find out that breakaway point? It is the break at this breakaway point, the k will be maximum for the real axis. So you can just take the derivative and equate to 0, and you found out that s to be equal to -2. So it is at this -2 it breaks off. Then we want to know in which direction will this root proceed as k increases beyond this value, beyond this -2. Now that can be found out by drawing an asymptote. So in order to draw the asymptote, you require two things. One is the angle of asymptote, other one is the meeting point of the asymptote on the real axis. Using this expression, we have found out this angle of asymptote and the meeting point. And in this problem, in this particular problem, this meeting point happens to be equal to the breakaway point. Therefore, this is how you need to draw. Okay, while drawing, you need to ensure that the anti-clockwise direction has to be positive. So 90 and 270 you have drawn. So since the breakaway point is equal to the intersection point, you can come to a conclusion that this particular root locus will exactly follow the direction of that asymptote. So now that you can draw over this asymptote the root locus, and root locus will be going in either of these infinities but on the half of the s-plane. So from this you can see that this remains on the left half as k varies from, so k always varies from 0 to infinity. These are the two starting point, right? So these are the two starting point we have seen already. These are the points where k is equal to 0. As k increases, these two goes, and at infinity, this is at the point at k is equal to infinity. This is the point at k is equal to infinity. So when k reaches infinity, this reaches the infinity but on the left half of the s-plane, ensuring that the system is always a stable system. Okay.